who is Marc Huertas-Company, who he's a staff at IAC. He's been a pioneer of machine learning applied to galaxies, working on this topic for almost 15 years already. He has been a professor in Paris, and he is now in IAC, and he will try to summarize all the findings that applied to of machine learning applied to galaxies surveys from the last decade. So Marc, whenever you want.
Hey, thank you very much. Yes, so I'll try quickly to give an overview of what's been the impact of deep learning applied to a very specific field, which is the field of galaxy surveys, which goes from galaxy formation to cosmology. And in particular, I will describe a little bit what are the main applications, because there are many, as opposed to what we've just seen in Nanda's talk. But especially, I would like to trigger a little bit the discussion afterwards. So give a step back and try to measure what's been the impact, or in some sense, of these techniques so far, and if we have learned something from applying them to data. So the context is the same as Andres mentioned, and it's basically the trigger of these. So galaxy surveys are mappings of the sky in which we observe a fair amount of objects, and the sizes of the data sets have been steadily increasing. So in the early 2000s, we have been entering what I call the era of statistics, in which we have going from dozens of objects to really statistical samples, close to 1 million of galaxies, and this allows has allowed a fair amount of progress, but still at the level in which, let's say, algorithm centric, in which you specify and you generate algorithms adapted or, for the specific purposes, because, you can still analyze samples in a fair amount of time. Now, things are evolving, as you know, and we are entering what I call the data-driven era in astronomy. And this, at least for the galaxy surveys, is obvious, with data sets coming like the Euclid survey or the LSST from the Vera Rubin Observatory. And one thing I would like to emphasize is that, the data-driven astronomy era is not only about bigger data sets, which is, of course, a problem, because we need to do things faster, and we need to be able to make inference on these large data sets, as Andres mentioned, but it's also more complex. So data are becoming of higher quality or higher dimensions. And we have been experiencing the emergence, for example, of IFU surveys, in which now we have, for each object, several tens of even hundreds of spectra. And so we augment the dimensionality of your data set, and also, better spatial resolution, as we are all waiting for these first images from the James Webb, for example. And so the response of the community to this has been looking into these data-driven approaches, which are, represented by artificial intelligence. I'm showing here a plot in which it shows abstracts in AstroPH with different keywords that you can see here in the legend. And you see, for example, galaxies and cosmology, the relative frequency of papers has become, basically in the last 20 years, constant. However, when you look at a keyword like neural, which implies neural networks, you see that from 2015. The increase in the relative increase in number of papers using neural networks has increased exponentially, and even much faster than other Bayesian techniques, for example, that were very popular, that started to be very popular at the beginning of 2000s. And so this is what I call the AI revolution, or what's happening, the deep learning era. And I would like to focus on this period here, what's happening here, and what I've learned from this exponential growth of publications. So why is this happening? Why from this increase in neural network and this interest? Of course, there's the data volume, but also, the machine learning community is coming from a long winter in which, very trivial tasks like recognizing cats and dogs in images remain very challenging for computers. And this has been the case for almost 50 years since the first machine learning techniques were applied. And so this has dramatically changed after 2012 with the first application of convolutional neural networks, and we have entered what we call, the deep learning era, or a new machine learning spring, let's say, after the winter. And now it's become trivial to classify objects, but we need to understand that this is still a simple task, and the point is that we come from far. But this has opened, lots of, possible applications and lots of ways of a different way of looking at the data. And so it's been basically a decade now that we have been using deep learning we are into this deep learning era. And so it's fair to ask, what have we learned, right? So it's been a decade of deep learning, and it's basically half a decade or 6 more or less years in astronomy since the first paper using deep learning. And so what have we learned so far? And I've divided here different types of applications and going from, more standard to, what I think it's is mostly accelerating and incremental science to other things that could be potentially new. And you can see that. So first application would be, really data processing. And this is very close to computer vision applications, basically out of the box applications of machine learning to data. And then there's been lots of machine learning techniques, deep learning applied to inference, to extract galaxy properties. And this is a focus in which we replace existing algorithms with a faster and more efficient solution because the data volumes. And there's also, in the emulation side, as also Andres mentioned, for solar physics, there's lots of, common applications here in which you try to accelerate the generation of cosmological simulations by populating dark matter halos. And then on the potentially new applications or things that can potentially, lead to discoveries or to new physics or discovery of new stuff. Are deep learning applied for discovery. So this means data exploration, and this is linked to the complexity of the data. You want to find structure in your data, identify new objects in these large volumes and complex data. You also want to find hidden correlations, so trying to extract properties of galaxies which are not directly observable, and so find correlations in your observables that allow you to go back to infer physical properties that are not directly accessible. And also you can go and use deep learning to really constrain the cosmological model. And so this means you bypass well-known summary statistics and try to constrain models using now all available data. So finding new signal of the models in data. And so I don't have time, of course, but I just want to highlight one of these examples of these different applications and then focus more on measuring the impact. So deep learning for low-level data processing. This is, of course, one basic example is classification. And we know that, and this is why deep learning has become popular, because it classifies cats and dogs. And so obviously this is where it's easier to be applied, and it's been applied massively. So this is, for example, to classify strong lenses, which are rare events, but which are very interesting to constrain cosmology. And so, but it illustrates well how we have entered the data-driven approach. So before deep learning, the way you will detect strong lenses is by, trying to identify manually by subtracting the light profile of the galaxy and so forth, trying to identify signatures of lensing, of arcs in your images, right? And so this means you need to build an algorithm that smooths, that detects the arc, and then selects, measures some properties, and you say it's an arc. And now, so what happens when you apply deep learning here is that you bypass all this algorithm focus and summary statistics, and you change these just by a neural network. And so you really move from an algorithm-centric focus to a purely data-driven approach. And I think this is a change of paradigm in the way we approach data, at least for this particular focus of classifications. And this is an example, but classification, deep learning for classification in galaxy surveys is huge. I'm putting here a few references. Of course, there's you can do galaxy morphology and so on. And the approach is always the same. Is you move from specific algorithms to just feeding images and getting classification. You can do deep learning also for inference. This is what I say, for measuring galaxy properties. And here the idea is, I want a fast, again, data-driven approach and with no summary statistics, and that allows you to measure galaxy properties. And typical examples are, for example, distances or photometric redshifts. Normally you use these by fitting models. And here, instead of that, you just try to learn the mapping between images and colors and photometric redshifts without, using the photometry and without using a model, explicit model. You can also use these for measuring, for example, parameters of strong lenses, not only detecting them, but also, you know, measuring the potential parameters of strong lensings. And so the idea is always the same. You will feed the data and you try to get parameters directly without a physical model. And again, the idea is that you want these to be faster and sometimes more accurate here, because, for example, in this particular case, you know, by using CNNs, you are also using at the same time morphology and photometry to infer photometric redshifts. I'm going fast, just some examples. Again, very popular, it has become the use of deep learning for emulating cosmological simulations. So cosmological simulations have become extremely necessary to understand and interpret our observations. Problem is that they are very expensive. And so again, especially if you want to introduce hydrodynamic physics. So what you can use here, neural networks is as an emulator. So you basically, again, is the idea of accelerating stuff. And so basically you run cheap simulations, which are dark matter only, and body simulations, which are only gravity, and are very cheap to run. And then you try to use a neural network to learn the nonlinear mapping between the dark matter simulations and baryonic quantities, like, you know, the temperature of the gas or the density, and so on and so forth. And so basically, once you have learned these from a subset of sub-simulations, you can just very quickly run cheap dark matter models and then populate them. And you can use these to do inference, which is, you know, extremely powerful. Now, moving a little bit to, you know, things that could be not accelerating, but, you know, potentially lead to discoveries. It's, you know, all the topic of trying to find outliers or find things that are potentially interesting. And in these large surveys in which we cannot look at objects one by one. And so the idea here is that an outlier is anything that you cannot model properly. So if you don't know how to model this, it should be something interesting. And the good thing is that neural networks are very powerful at modeling complex systems. So you can train, in that particular case, this is for LSST, this is transients. So you're trying to look for transients or, you know, light curves that are out of the norm. And so basically you use here a type of architecture that allows you to build or to learn how to mimic, generate different types of light curves. And then you see if you are not able to reproduce one of them, then you say it's an anomalous one. And so this is a way of filtering the data, let's say, and assisting the discovery of new objects, which, you know, it's something that could be potentially very interesting. And again, there's lots of papers looking at this. Also in this discovery thing, and also, you know, a bit more proof of concept, but is the idea of going a step beyond and you know, learning equations, which is basically what we do as physicists. So you have the data and you have to try to explain what's in the data with a few numbers and equations, right? And people have been trying to do that with graph neural networks, for example. This is just an example of trying to understand how the dark matter over density it can be described based on a dark matter simulation. So you describe the nodes of your graph neural networks are the halos, and then you describe the relations between the different halos, and you try to understand what's the equation that's behind these. Finding, again, potentially new is, you know, finding hidden correlations, things that we don't know how to do otherwise than with machine learning, or because, you know, the mapping is too complex. And for example, one example is identifying galaxy mergers, let's say, because galaxy mergers we know are dynamical processes, but we don't know when we observe a snapshot of a galaxy merger, we don't know in which phase it is. And so basically it's a kind of inverse problem in which you want to know when the merger started, for example, or where the merger is going to end, because this allows you to put some dynamical time and temporal information into your data, and then correlate these to other properties. And so you can do this inversion with simulations in which you have lots of snapshots of different mergers, and then you can make the neural networks make this mapping between this movie and a single snapshot, for example. And this is something that it's difficult to do without with traditional approaches. So we are basically finding hidden correlations or information in the data. People are even pushing this a bit more, and this is a bit speculative, but you can even invent new data instead of going to the telescope. Let's say we know taking images is easy, it's cheap. Taking spectra for all objects for galaxies is much more expensive. So you can have a neural network that emulates a telescope, and basically from some sets of images, it produces a spectra. What would be the spectra of these galaxies? So basically, it's a massive interpolation. But if you have enough data, these works show, for example, that you can sort of reproduce reasonably well the spectra of different galaxies without observing them. So this, poses some interesting questions, but it's another way of, finding information in the data that otherwise it's difficult to find with traditional approaches. I'm moving fast and to my last, point, which is, using deep learning to constrain our cosmological model. And basically, we know how to constrain cosmological model, by example, by using summary statistics or 2-point correlation functions. And this is what we typically use. But by using these, we are throwing away lots of information. So again, we are using here deep learning to find new information in the data. And this is, for example, a nice example of this, in which these people have shown that with only properties of a single galaxy, let's say the velocity, maximum velocity, rotational velocity of a galaxy, stellar mass, metallicity of one unique galaxy, you are able to constrain the omega matter, the dark matter content of the universe. And so this means that there's some information imprinted in the properties of the galaxies that tells you about what's the underlying cosmology at very small scales. And this is again discovering something that it's not trivial to find, or that we didn't know about. And you're using, more information to constrain additional models. Okay, so in the last minutes, I want to, trigger a little bit the discussion afterwards, and go a step back, and so trying to understand how these, what's been the impact and how these deep learning techniques have been entering the community. And so here I'm just giving an overview of the different groups I've been describing, and how the different machine learning techniques that have been used, modern deep learning techniques. And one thing, a takeaway message of this is that, in general, our community uses the latest and state-of-the-art techniques quite rapidly. So there's a bit of delay between the time it goes into the machine learning community and the time it penetrates our community. But the fact that we are using, state-of-the-art, this means that, there's a general good transfer of knowledge between this machine learning community that goes very fast and our community. However, one thing that happens is that in general, we are still at the stage in which you use very little domain specific adaptations. So basically we take developments in the machine learning community and we adapt it to our problem. And we just apply it to our problem without, really adapt. And this probably reflects the fact that we are not fully machine learning experts. It's easy to use, we can apply it, but it doesn't mean that we properly understand what's going on. One other thing that you can see from this table over here is that when there's a star here, is this, that you basically are training on simulations. You are informing your neural networks with simulations. And so this is common, I think, to many fields in astronomy. In many, we rely, because we don't have that many amount of labeled data, and we don't have, and the data is noisy, we rely many times on simulations. And this is, entails some risks, but you can see that it's overall everywhere. Now, we've seen there's lots of papers, but what's been really the impact? And so these are some statistics I've been doing in the past days about just grouping papers in the different groups I've told you about. So from processing, low-level data processing, galaxy properties, acceleration, getting hidden correlations, discovery, and cosmology. And this shows you as a function of time. So starting in 2015, the number of papers, for example. And you see that, the majority of the papers are still at the very low-level data processing. And if you look at what are the impact of these papers in terms of citations, you see that also, most cited papers are really low-level data processing. So the basic computer vision applications. Others are increasing, but they remain below. And one interesting thing that you can see also is that, there's a huge increase of data processing in number of papers, but now, it's plateauing. So basically, we are done with exploring basically different techniques, and the same trend is probably will happen in other applications. If you plot these now in another plane, which is now a number of papers in the x-axis and normalized citations, so citations per paper, you see again that it's low-level data processing that really outstands. So basically, what this is telling us that most of the impact of deep learning is still on basic data processing, and so this is basically incremental science. We are just classifying cats and dogs. However, despite an increasing trend, so this means that despite an increasing trend of papers, popular interest, we see potentially novel applications still have a low impact in terms of citations. For example, we see there's lots of paper aiming at discoveries, but the number of citations is low, very low. So why? Possible reasons, but I'm happy to discuss this, is that in fact the majority of new data sets in which we want to apply these methods have not arrived yet. So we are waiting for Euclid, LSST, Roman, James Webb. So it's basically preparation work. So it's normal that we haven't discovered anything yet. It's also that it's too young still. So it's maybe just a matter of time. So these curves that I'm showing about impact are just delayed, and we are still at the proof of concept stage. It could also be more fundamental problems, is that as we have been also, as Nand has been mentioning, that some key issues remain unsolved. And so there's still lack of trust of the community. And so this is, some key challenges that remain unsolved. And in fact, I've listed here also, and I will end with that, some current challenges that in fact we are facing in this machine learning community when applied to physics, with some references, and people are looking for solutions, but still are these questions that are preventing maybe, or these techniques to really have more impact. And of course, you have this problem of when you have small label data sets, people say, I don't want to use this, I don't need it. So there are some solutions. A big challenge is uncertainty estimation, but things are becoming better and better with Bayesian approximations of neural networks. We have power density estimators as well. Another huge problem is the black box problem, what we call interpretability. And there are also ways of opening the black box, but still, depending on the complexity, it might be still a bit limited. And we have, because we need to train on simulations, we have also this problem of domain shift, which in machine learning can create problems as well. So these are challenges that need to find a solution, and perhaps will help in increasing the impact of these techniques. So I will stop here with asking, trying to give some elements of answer to this question: is it a revolution or is it just incremental science? So one of the take-home message is that deep learning has rapidly penetrated the field of extragalactic astronomy in particular surveys. So it's been tested in many fronts. State-of-the-art ML techniques are rapidly tested. So there's a good, transfer of communication between the ML community and our community. And this is essentially driven by the fact that they are easy to use. They are libraries, and so it's easy to apply a new algorithm. Doesn't mean we understand it. It's easy to apply. Still, the most impactful applications are at very low level, out of the box. And this is basically classification and segmentation and derivatives at the pixel level. But it's not, new science that we are doing. It's basically incremental science. And it doesn't mean it's not useful, but this is, basically it's accelerating science. And this is where it's more popular. So potentially novel applications have emerged. So people are testing them, but remain at the proof of concept stage with moderate impact for now. And so with this, I will stop, and I'm happy to trigger the discussion on these topics if you're interested.
Thank you so much, Marc, for this detailed description of the surveys and the state-of-the-art techniques. And thanks also for staying in the time. We have a few questions in the chat. So Benjamin Montesinos asks, concerning these hidden correlations, do the algorithms allow you to get some deep physical insight into the nature of those correlations, or they just tell us that there is a correlation, but without giving any additional information about what physical features the algorithm has correlated?
Yeah, so this is a good point, Benjamin. So in fact, there are the two of them, and people are looking at both. So they are trying to just, that there's a correlation, you can stop there, but people are trying to understand where this correlation comes from. For example, in this plot I've shown, for example, in trying to infer cosmology with just one galaxy, this is an example in which already you're ranking which is the parameter that is most relevant to why you know, a single galaxy tells you about the cosmology, and you see that it's a rotational velocity. And in fact, what they show in this paper is that you start looking at these parameters and you find that there's, you know, the cosmology imprints a specific relation between, you know, the dark matter and the rotation of stars, and then so you find a plane, and so basically you can do it a posteriori, let's say. So it's not that you directly know what happens, but you can explore. And then if you want to move a bit forward, there's this idea of, you know, doing some symbolic regression and trying to find a formula, which is also a way of, you know, opening the black box.
Great. Guillaume Thomas asks, referring about the plateau we saw on the number of publications for processing a data set, if that plateau may be caused by the COVID lockdown, which you can see in many different classes.
Yeah, could be, and this, I don't know. I see that this plateau is, you know, is happening, you know, maybe you don't see that in all of them, but it's true that it's plateauing a little bit. So this could be driven by that. I don't want to overinterpret this. So maybe we need to wait a little bit.
And Carlos has a question about convolutional neural networks applied to the classification of galaxy images. And he's asking if there is a way to give us an input to the CNN images which have different pixels as input. Otherwise, if you have a fixed pixel size as input, noisy images from small, faint, distant galaxies, and you will have degraded images for the large galaxies. Is there any new techniques which allow you to bypass this issue?
Well, yes, there are. I mean, you can, if this is a problem, you can indeed work around it with different ways. For example, people are now moving to use also transformers or a variant of, you know, vision transformers, and this allows you to deal with different sequence or sizes, for example. You can play different tricks as, you know, also having different branches for your CNNs if you want, depending on the resolution. So yeah, I think you can bypass this. Indeed. It's not a fundamental limitation, let's say.
Great. We have another question from Guillaume. So you said astronomy relies a lot on simulations to train machine learning. Do you think that in the coming years, we will see a strong increase in the use of transfer learning methods? They might also be useful to understand better the noise in observed data sets.
Yeah, indeed. So this is a main issue with, and this is one of the big challenges here, which is called the domain shift. Fortunately, this is not the only field in which this happens, but in astronomy is extremely relevant because, you know, we really always tend to train on simulations. And what happens is that simulations are not perfect. And when you train a black box, a nonlinear black box, let's say, on something, and then you apply it to another thing that's a different domain, you can have strange behaviors. So there are ways of bypassing these, but you know, people are still testing them. Transfer learning is an option in which basically, if you have a subset of you know, observationally measurements in observation, that you can trust, then you can refine your neural network. Other approaches are domain adaptations, for example, which is in which you don't need any label data set or from observations, but you just, during training, you make sure that the features that your networks extract are non-specific and not specific to the simulations by showing some observations at the same time. So, but these things arrived slowly, but indeed, you know, these are some, I think, some key challenges that prevent these methods to really be trusted, but they are coming.
Great. We have another question from Jorge Sanchez Almeida. He's asking if there is an alternative way to treat large data sets from apart from artificial intelligence.
Well, this is a good point. Andres made some nice points, but I will ask the question in the other way. Do we really need to treat large data sets, and why? Because there are some, you know, for some science cases, you might need them. For example, if you want to do really, you know, cosmology, lensing, indeed, you need these large areas. although as we can see with one unique galaxy, you can provide some estimates. But, you know, for galaxy science, for example, do we really need to go from 1 million to 10 billion? Are we learning something? And this is, instead of saying, I think, is there any other alternative? Probably the question we need to ask is, do we need to treat 10 billion galaxies? And are we aiming to learn something else? Because if it's just, you know, to do incremental science, okay, it's interesting, but maybe you're not learning anything. So